let's do a few more applications of these substitutions formula. And maybe also give some definitions, some important definitions. So let's do this. You remember that's something we began by saying. What does it mean to compute this thing when you're in 2 dimensions? Okay, that's going to give you the volume below the surface. Well, and you make it you make it a signed volume if ever the function takes some negative value below the surface given by z is equal to x to f of xy, and above area d of the plane of the xy plane. Okay, so what do you think is happening when you're computing this thing, this constant one function on some domain D? That's going to be the volume below the surface of constant value 1 and above domain D. But you know that this volume is given by area times the height. Okay, so as the height is equal to 1 here, that gives you the area of D. Okay, so that's very nice stuff. What else can we get from that? Volume of, well, similarly, the volume of a region of R3, well, it will be given by integrating one function on well, the volume that you want to compute on this region that you want to compute, dx, dy, dz. Okay, what else can we get? Oh yeah, just one more simple definition. The coordinate of the center of mass, coordinates of the center of mass, that's going to, of a 2D surface, they are going to be given by well, xm and ym, and you can use 1 over area of d times x dx dy of on d, and 1 over area of d times, sorry, that should be here, y dx dy. Okay, so let's do some very simple applications of these definitions. Okay, maybe we can begin with well, oh right, slice of a pizza. Okay, slice of a pizza slice. A slice that would be angle theta 0, that would be angle theta 1, and I want the area of the pizza slice. So you know it's going to be very simply given by the integral on, so let's say that this is d on your pizza slice of the 1 function, okay, 1 dx dy. But I can't really well describe my my domain using Cartesian coordinates. Well, on my drawing it looks like theta 0 is 0, but really let's make it like this. Let's take some pizza slice over here so that we get a non-zero theta 0, and makes it harder to describe using Cartesian coordinates. So you know that you should go to polar coordinates. In polar coordinates, let's say that your pizza has a radius, well, let's call that r, okay, and so your area is going to be given, well, we do the substitution to polar, so obviously we're going to have well, theta is going to go from theta 0 to theta 1. That's just given by the description of my area. And then rho goes from 0 to r. And I've got 1, which just remains 1, but I get rho d rho d theta, except that I wrote the bounds for theta first. So that's rho d theta d rho. Okay, and so let's compute that. So between 0 and r, so rho times theta 1 minus theta 0. Okay, don't hesitate to stop and do the calculations. D rho, so that's 1 over 2 rho square times theta 1 minus theta 0. So between 0 and r, so that's 1 over 2 r square theta 1 minus theta 0, which we sort of expected, okay, because that's just a very even portion of your um, of the whole disk. Okay, if you want to impress your friends, you can also compute the coordinates of the center of mass of your pizza, assuming the toppings have been evenly distributed, and then try to make it turn over the tip of your finger, right, once you found it. So you would just apply xm is 1 over what we found earlier, that area, 1 over 2 r square theta 1 minus theta 0 times the integral on, well, the same stuff, so theta 0, theta 1, 0, or of, this time we get x, so in terms of polar coordinates, that should be rho cosine theta times d, well, again, d theta d rho. So, and you get the ym coordinates by, well, same stuff, except that here, instead of rho cos theta, you get rho sinus of theta. Okay, and, well, I guess you can compute that by yourselves. That's a very good exercise. Let's also, while using the same those formulas, let's compute again the volume, some volumes. So let's say the volume of a sphere of radius capital R. Oh, sorry. So what do we get? We said that this volume will be given by whatever I can use to describe this volume, this region of 1 dx dy d theta. And, well, obviously a sphere calls for spherical coordinates. And so, oh, sorry, dx dy dz. And so I'm doing my substitution with spherical coordinates. So I get, so my function is still going to remain 1, but I have to change my bounds. I'm going to have, so, I've got phi, I've got rho and theta. Okay, so you remember we had found that dx dy dz would be given by rho square sine phi d rho d phi d theta, and so I get, well, if the first one is rho is going to go from 0 to r. Phi should go from 0 to pi, and that's a pi, and theta goes from 0 to 2 pi. You remember, you need only one of the angles to just do half of the trigonometric circle in order to describe everything we need. Okay, so that's about it. So we just have to do it calmly. So let's do the integration. So let's integrate with respect to r first. So I got the outer integrals. Oh, just by remaining the same ones. And I've got so sine phi that can go outside, and then I've got 1/3 or 3 coming from the integration of the rho square d rho on r and 0. Okay, so that's what it's giving me. And then I have so d phi d theta, that's just going to be so I've got so sinus of phi becomes so I still have my outer integral, so let's say it's one at a time. The sinus of phi becomes minus cosine phi. Okay, excellent. That's what we need. From 0 to pi, I still have my 1/3, 3. And so I still have my d theta. So my minus cos phi in pi, that's going to be minus minus 1, so plus 1. Minus minus the value in 0, so plus 1 also. So that's 2. Okay, so and finally I've got the integration on of theta on 0 to pi, but nothing depends on theta, so it's just going to be 2 pi. So 2 pi times 2 times rho or 3/3, and you find again the formula that maybe you had forgotten for the volume of a sphere. Okay, so that's it for some very simple applications. We're going to go a bit further in the worksheet.